Hello everyone, I am Nirajan Koryala and today I'll be presenting Summation-based private segmented membership test from Threshold-FullyHomomorphic encryption. This is a joint work with Jonathan Takeshita, Jeremy Stevens, and Teho Zhang. Firstly, I would like to go a primitive called private membership test, where we have a receiver with a query element y who is trying to check if y is contained within a larger set x held by a sender. The receiver should not be able to infer any information about the sender set elements, and the sender should not be able to infer anything about the query element y. In this work, we extend this problem to private segmented membership test, where we have multiple senders and the receiver is checking if the query element is contained within the union of these sets held by the senders. Some requirement of PSMT problems are that both receiver query and the sender set should be encrypted throughout the process. We provide provenance privacy. That means the receiver is not able to infer which set the intersection is coming from. We provide support for a very high number of senders, potentially thousands, and we operate under a semi-honest setting. Some applications of PSMT ranges from tax authorities trying to identify any tax evaders with accounts in both domestic or foreign banks, and banks themselves trying to screen customers against fraud lists, and different government entities trying to collaborate together to compute over encrypted databases to protect personally identifiable information of the customers. Going over one example of PSMT, you can see when a passenger is trying to enter a country, a TSA officer might be interested in checking if the passenger is included within watch list of any other government agencies held encrypted. So the TSA officer would use a unique identifier of the passenger to perform the PSMT test with the watch list and then verify if the passenger is able to enter or not. Some existing solutions that provide really fast methods to solve the PSMT problem include private sender intersection, multi-party PSI, or private membership test. PSI in particular, we have asymmetrical PSI, which is a pioneer FHE-based PSI, and provides very fast solution to the PSMT problem. And similarly, there are other works under MPSI and PMT as well, which provide solutions. However, these solutions are only useful for only a specific use case scenario and provide only partial solutions. In particular, they lack scalability, provenance privacy, and require the senders to hold the sets in plain text. Now we go over how existing FHE-based PSI works. So basically, this receiver sends an encrypted query to the sender, who computes this intersection polynomial using the query, and you can see the sender set is in plain text here, and then send the query back to the result back to the receiver, who checks if the result is 0 and confirms an intersection, otherwise a random element R. As you can see here, this intersection polynomial requires all the ciphertext from different senders to be multiplied when you are trying to aggregate them, and this is a fundamental limitation, as it increases the multiplicative depth in a logarithmic fashion, even if we are using very efficient techniques like binary tree to multiply them together. Our idea is basically to compute a different polynomial where we are able to summate the results from different senders so that we get infinity when there is an intersection, and we keep the multiplicative depth to be constant even when the number of senders are increasing. So compared to the previous approach, this is how our idea differs, and some challenges that we need to solve to make our idea practical. It's basically computing the division operation, which can be very costly in FHE, finding a function to approximate this kind of behavior, as infinity doesn't exist in FHE, and similarly approximating the function over a large domain to support a large number of sets. Uh, so this takes us to value annihilating functions, which is basically a function which maps 0 input to some large value and all other inputs to 0. So in this example, etan is a VAF, and after computing etan, we are able to check the result for an intersection of or non-intersection depending on the output, which is equal to k or not equal to k. Now, as you can see here, there is a branching operation occurring here, which is very hard to compute in FHE. So we need to approximate this function. We found that derivative of hyperbolic tangent is a perfect candidate for approximating this kind of behavior. However, naively just approximating this function over large domains can be very expensive and require extra time and very extra FHE depth, and also the approximation might not be also highly accurate if only Chebyshev based approximation is used for our application. To solve this high domain problem, we use domain extension polynomial. So domain extension polynomials basically shrink a large domain interval into smaller subintervals such that property of VAF around 0 in the smaller domain is preserved. So using the APs, we are able to shrink the domain and then perform Chebyshev on the shrink domain, so that we only require smaller parameters to perform the approximation. As you can see, this is an example of DEP where we have shrunken the domain into a range -1 to 1, where it is very accurate in that specific subinterval. After the approximation, here are some optimization that we enabled for our protocol. The standard one is FHE batching, where we encrypt different vectors within a single ciphertext to increase the throughput. To reach the false positive, or we basically get rid of the contaminated values by applying a square and scale technique. We also provide parameters for DEP and Chebyshev to support very large sender sets with minimal FHE depth. So in our final protocol, we assume the receiver and senders are given partial encryption keys and homomorphic evaluation keys. Receiver basically encrypts the query element and sends it to the senders. Senders then compute the subtraction, apply the DEP procedure, then evaluate the VAF, which is etan, over that subtraction using Chebyshev-based approximation. They finally perform the homomorphic scaling test and scaling operation to eliminate any contaminated values. Finally, a leader sender summates all those values, aggregates them as a random non-zero element, and sends it back to the sender and the receiver for partial decryption. The senders perform the partial decryption and add a smudging noise to ensure INDCP-AD security and transmit it to the receiver. Receiver completes the decryption using his share of the partial decryption, and then confirms if there's an intersection if the summation crosses a predetermined threshold tau. Now for the evaluation, we implemented our protocol and APSI protocol with multi-party support using OpenFHE. We also employed CKKS parameters to ensure 128-bit computation security and 36-bit statistical security. For the scalability testing, we observed that for the small number of senders, our protocol is slower than the other state-of-the-art protocols because of high time required to perform the approximation. But as the number of senders grew, we observed speedups of almost 6 times for a number of senders equaling 4,000. And in the graph below, we can also see that for individual operations, our protocol is slower than Kong ETL here. However, considering the total time, our is much faster than the Kong ETL protocol, which is in the red and orange line over here. Going over to the communication overhead, we are a little bit slower in terms of communication compared to the other protocol, as we operate on encrypted datasets. However, considering high throughput networks such as 1 gigabit per second, our protocol is on par with other existing state-of-the-art protocols. This is especially true in case of applications such as banks or TSA, which are equipped with high throughput networks. For the overall computation, including computation and communication, we are almost 2 times faster than the existing state-of-the-art Kong ETL protocol in case of 10 gigabit per second speed, and for 1 gigabit per second speed we are almost 0.8 times faster. So in conclusion, we introduce a new primitive and enable variant optimization to make the protocol practical, and demonstrated high scalability and also ensured NDCPAD security. In the future, we would like to support multiple query items, reduce the communication, and also handle malicious PSMT based on Threshold-FullyHomomorphic. These are some references. Thank you for listening to this talk.